Hi everyone, my name is Ardiani Shazwin binti Haiza. My matrix number is D202010949696.
Hello everyone, my name is Jurina binti Maulana. My number matrix is D2020109570.
Hi, my name is Nur Alia Saleha binti Fauzi. Matric number D202010956616.
My name is Nurul Atika binti Masaha. No matric D202010956673.
Hello everyone, so let's take a look at my Gauss-Seidel coding. So as we know, Gauss-Seidel can solve the linear and square matrix. So now we have A matrix, which is we have 3 by 3, which is square matrix. So now we have 5, -2, 3, -3, 9, 1, and the third row is 2, -1, and -7. And then for the B, we have -1, 2, 3. And for the initial X, we have 0, 0, 0. Before I start with the calculation, here I just want to remind the real formula for the Gauss-Seidel, which is X equals to D minus L inverse, multiply with U, and multiply with X power to K minus 1 plus D minus L inverse and multiply with B. So here I start with find the diagonal first, diagonal of A. And for the diagonal of A, we have 5, 9, we have 9, and we have -7. Okay, but I want to show it in matrix, so I have D2, and we arrange the diagonal in the matrix. We have 5, 0, 0, 0, 9, 0, and 0, 0, -7. Okay, so now we want to compute the L in the formula. So I have NL equals to lower triangularize A, which is we want only the lower part of A, and we want to exclude the diagonal. That's why I minus with D2, and then we will get strictly lower triangularize. We have 0, 0, 0, -3, 0, 0, 2, -1, and 0. Okay, so settle for L, and after that we want to compute for U. So for U, I have upper triangularize of A minus with D2. This one upper triangularize of A, meaning that we just want the upper part and we want to exclude the diagonal. Okay, and then we will get strictly upper triangularize. And then the answer is 0, -2, 3, 0, 0, 1, and 0, 0, 0. But in the definition of Gauss-Seidel formula, the L is minus NL. So U is negative NU. So that's why I write in this form according to the definition. And for the last calculation is ID. ID, which means I want to settle for this one, D minus L inverse. Okay, so that's why I write inverse of D2 minus L, which means D2 diagonal matrix minus with L. My L is negative NL, which is the strictly lower triangularize, and then I will get this one, D minus L inverse. Okay, so this is the answer, and after make the calculation, I just want it to make the iteration. I use for loop. Okay, for the initial of X is 0, 0, 0, and then start with 1. The iteration I make just less than 10. Okay, so this is my formula according to my variable in this coding, but actually I just modify this formula from the original, this one. Actually it has the same meaning, and then we will get the iteration just like this. from my observation, so start from iteration 1, 2, 3, 4, 5, 6, 7 and 8, we will get the same value. The value will get the same, start from iteration 8. And I just want to show in this video that we can use every type of loop. This one I use for loop, but here, right here, down here, I use do loop. And then I just want to show we will get the same answer. We will get the same answer, which is at iteration 8. Okay, we will get the same value. Here I do the iteration in 6 decimal point, but if we do in 3 decimal points, we will get 1, 2, 3, 4, 5. We will get from the iteration, from 5th iteration, we will see the value will start converging.
Hello everyone, let's take a quick look at the answer for Jacobi method coding. So this is the coding for Jacobi method. We can see here that the iterations start to converge at the 12th iteration. Okay, so based on the previous explanation, we can see that the Jacobi method converge at 12th iteration and Gauss-Seidel method converge at 8th iteration. In terms of speed, the comparison is Gauss-Seidel method faster than Jacobi method due to the use of updated components in the same iteration. Meanwhile, Jacobi method slower than Gauss-Seidel method due to independent updates of each component of the solution vector. Hence, that is the reason why Gauss-Seidel method converge faster than Jacobi method. Other than that, Jacobi method uses more memory than Gauss-Seidel method as it stores 2 solution vectors for each iteration. Meanwhile, Gauss-Seidel method uses less memory than Jacobi method as it updates only one component of the solution vector at a time.
Next, I am going to explain about the steps taken to solve linear equation using Gauss-Seidel method by hand. Here we have the linear equations, which is 5x1 minus 2x2 plus 3x3 equals to negative 1, negative 3x1 plus 9x2 plus x3 equals to 2, and the last one is 2x1 minus x2 minus 7x3 equals to 3. First, I have the initial approximation of x1, x2, and x3 equals to 0. Then, I rearrange the equation in terms of x1, x2, and x3. So, the new equation will be x1 equals to negative 1 plus 2x2 minus 3x3 divided by 5, x2 equals to 2 plus 3x1 minus x3 divided by 9, and x3 equals to 3 minus 2x1 plus x2 divided by negative 7. After that, we will start to calculate the first approximation for k equals to 1 to find the value of x1, x2, and x3. We substitute the value of x2 and x3 equals to 0 into equation that we have already arranged as our initial approximation is equals to 0. Then we will get x1 equals to negative 1 plus 2 multiplied by 0 minus 3 multiplied by 0 divided by 5. Then we will get the answer negative 0.2. Next, to find x2, we substitute the updated value of x1 equals to negative 0.2 and x3 equals to 0. The equation will be 2 plus 3 multiplied by negative 0.2 minus 0 divided by 9. Thus, we get x2 equals to 0.156. For x3, we substitute updated value of x1 equals to negative 0.2 and x2 equals to 0.156 into the equation. the calculation will be 3 minus 2 multiplied by negative 0.2 plus 0.156 divided by negative 7. It will give the value of x3 equals to negative 0.508. Based on the slide, I continue calculate the second approximation with update value of x1, x2 and x3. Hence, it will give x1 equals to 0.167, x2 equals to 0.334, x3 equals to negative 0.423 for the second iteration of k equals to 2. We will continue calculating until all approximation converging. It is important to use the updated value of x1, x2 and x3 in the same iteration because we are using Gauss-Seidel method. Last but not least, I have calculated the rest iteration and put them in the table. As we can see, the values start converging at k equals to 5 and k equals to 6 as they form the same set of value for x1, x2 and x3, which is x1 equals to 0.186, x2 equals to 0.331 and x3 equals to negative 0.423. Thus, we can conclude that by using Gauss-Seidel method, the iterations start converging at k equals to 5.
So in this slide, I'm going to compare between these two methods, which is Jacobi method and Gauss-Seidel method. The equation here is 5x1 minus 2x2 plus 3x3 equals to negative 1, which is the first linear equation. The second linear equation is negative 3x1 plus 9x2 plus x3 equals to 2. And the third linear equation is 2x1 minus x2 minus 7x3 equals to 3. And the variables here we have are x1, x2 and x3. So here is the comparison between these two methods. In terms of convergence, the Jacobi method had converged at the 7th iteration for x1 equals to 0.186, x2 equals to 0.331 and x3 equals to negative 0.423. While for Gauss-Seidel method, it converged at 6th iteration, which is x1 equals to 0.186, x2 equals to 0.331 and x3 equals to negative 0.423. This shows that the Gauss-Seidel method will converge faster than Jacobi method. So next, the comparison between Jacobi method and Gauss-Seidel method is its speed. Jacobi method slower than Gauss-Seidel method due to independent updates of each component of the solution vector. As we can see, for the first approximation in Jacobi, we have to substitute 0 for all linear equation first. Then after that, we substitute the updated of each component of the solution vector in the second approximation. While for Gauss-Seidel method, it is faster than Jacobi method due to the use of updated component in the same iteration.